David Paige, who is a professor of planetary science at UCLA. So David, go ahead as soon as your talk is up.
Thank you very much. In my talk, I'll be describing the results of the Diviner Lunar Radiometer experiment. I'm supposed to be presenting from UCLA rather from David Paige. Can you switch me over to that?
Yeah, we'll make UCLA presenter and then start that webcam if you can.
It's on.
Start my webcam.
Oh, start my webcam. Okay, there we go.
Now in the middle.
All right, here we go. Excellent, thank you.
Great, thank you.
There we are. All right.
Perfect.
Where do I click the slide? There we go. Thank you very much. So I'll be presenting the extended mission results from the Diviner Lunar Radiometer experiment on LRO. All right, here we go. So Diviner is a 9-channel infrared radiometer. It has a field of view of roughly 250 meters per pixel on the surface. Its channels cover both the solar as well as much of the infrared spectrum. The original science goals of the instrument when we proposed it were to characterize the moon's surface thermal environment. The moon has a very diverse thermal environment between daytime, nighttime, as well as polar. Also to map the properties of lunar surface, the bulk thermal properties, rock abundance, and its composition, and also to characterize the moon's polar cold traps. That includes mapping the locations and temperatures of these cold traps, assess the potential for volatile lunar resources, and determine thermophysical properties. We've been mapping now for almost 4 years, and in this time, we've accumulated quite an extensive data set, and we also learned a lot about how to use our data to find out more about the moon. In the talk, I'll sort of talk about our efforts in this area and how we're progressing. The LRO makes one map of the moon every month over 360 degrees longitude. This gives us a daytime and nighttime map, and examples of these maps are shown on the left side of the slide there. You can see that the strong difference between the daytime and the nighttime temperatures, as well as the extreme temperature contrast that we see in the polar region. Diviner's now been mapping for nearly 4 Earth years on a continuous basis, both day and night. And by the end of this month, we'll have gotten something on the order of 104 monthly global thermal maps of the moon. This is by far the most complete and extensive multispectral thermal emission measurements that's ever been obtained for an airless body. And it's unique because the local time of each of these maps goes through a complete cycle once per year. So we have, at any given location on the moon, data at almost any local time of day, as well as in the polar regions at multiple seasons. There's something on the order of now 250 billion individual radiometric observations with geometry that have been obtained. This translates to an uncompressed size of something like 100 terabytes of data and 40 million archived data files. So it truly is an impressive data set. Some of the highlights of our archive data products include, of course, reduced data records. We also have gridded global polar and global thermal maps. We also have a bunch of products that include rock abundance maps, nighttime soil temperature maps, global silicate mineralogy maps. We're also working on a recalibrated foundation data set, which will improve the accuracy and completeness of the data set, as well as a bunch of special data sets, including points of interest such as the Apollo landing sites, L-cross, Grail impacts, eclipses, Earth scans, etc. In my talk, I'm going to organize it about the science goals of the LRO extended mission. As John Keller described earlier, we're about something like in the middle of our first year of a 2-year extended science mission. And LRO in our plan has outlined a number of science goals that many of the LRO instruments will contribute to. And what I'll do in my talk is sort of highlight how Diviner is currently contributing to these goals. Of course, the mission's not over, and we're still in the middle of some of these experiments. I'll also highlight other talks and presentations that will occur later on at NLSI that will be relevant to these goals as well. The first major goal that Diviner is contributing to is the nature of volatiles deposited in the moon's polar regions. Our main contribution here is to vastly increase the amount of data that we get and observe the lunar poles at a wide range of local times and seasons. There'll be a talk tomorrow by Elliot Sefton-Nash that will talk about our polar mapping results in greater detail. What you see here are examples of some of our maps. These are annual maps of annual maximum temperature, average temperature, and minimum temperature in the south polar region. And these are very important because volatiles, of course, are the stability volatiles are determined primarily by their temperature, and Diviner is able to map in detail both surface temperature and then through models constrain subsurface temperatures. We can basically then determine which volatiles will be stable in which locations, and this is useful for that type of work as well as to guide efforts by other instruments to actually detect volatiles. Another thing we've been doing is looking in conjunction with other instruments is what we can learn about the actual distribution of volatiles. Dave Smith showed some Diviner data, so I'm sure you won't mind if I show a little bit of LOLA data. On the left is a map of the annual maximum channel 8 brightness temperature for the region from the South Pole to 70 degrees latitude. And on the right is a map of the LOLA normal albedo, which is done through taking the reflectance of the LOLA laser pulse and mapping it onto the surface. This is a new exciting data set that they're working very closely with the LOLA team on analyzing. The idea here is that analogous measurements on Mercury show that polar deposits there, where you have surface ice exposed, are quite bright. And the question is, can we find similar deposits on the moon? We're using the Diviner data to help interpret this because the data from LOLA also have a lot of geologic variations as well. And so we're working on disentangling the results and noticing some very tantalizing correlations, but this work is ongoing, but we should expect to see some results later this year on this. Another major goal of LRO during the extended mission is to look at the moon from the standpoint of terrestrial planet differentiation and early evolution. Diviner is contributing a lot of things in this particular area. One area of interest is using Diviner data to map to estimate the polar heat flow on the moon. The basic idea here is that there are regions at high latitudes that never receive any direct sunlight, and as a consequence, they're extremely cold. Diviner's map temperatures in some of the coldest places at the coldest times of the day and year down near around 20 Kelvin. In this sort of scenario, the only heat source that is keeping these regions warm is the heat flow from the interior. We've been able to do some preliminary work to use Diviner's minimum temperatures to estimate this heat flow rate, and we think we can get some results that could then add to the other measurements that have been made at the Apollo landing sites. On Thursday, Matt Siegler will be giving a presentation that discusses reinterpretation of the Apollo heat flow measurements in the combination with using Diviner data and thermal models. So look for that work as well. In addition to that, we're also looking at the moon from the standpoint of volcanic deposits. At this meeting, there'll be a presentation from Carl Allen on Wednesday and from Kristen Bennett looking at pyroclastic deposits. Diviner data can provide unique insights into the composition and diversity of the deposits, and then combining that with M-cube data and, in the case of Carl Allen's talk, GRAIL data, we can learn much more about the distribution, diversity, and origin of these deposits around the moon. Another thing we've been doing is looking at Cratered Central peaks. This is an area where we have a potential probe into the interior of the moon. It has been hypothesized that these ought to show some evidence of mantle composition. We've looked at quite a number of these, and typically they do not show composition that's more mafic than typical Mare basalt. And as far as we can tell, that these Cratered Central peaks do not appear to be sampling into the mantle, which of course is valuable for planning future missions. Does anybody see my? I seem to have lost track of my. Maybe if you want to put the slides for me here, I think. There you go. The next major goal of LRO is to look at the lunar impact record and its relation to solar system history. Bill Hartman talked about this in his medal talk, and it was very interesting to hear his sort of perspective on this. Diviner, next slide, is contributing to this work by doing a bunch of things. One is that we're able to, by looking at nighttime spectral differences, map quite accurately the global rock abundance. Generally, the surface of the moon does not contain rocks because small impacts, which are occurring constantly, are pulverizing the surface, creating a low thermal inertia surface layer. However, when large impacts occur, they can dig down into the lunar megaregolith and then expose blocks on the surface. And in the top left-hand portion of this plot, you'll see that there are a series of Diviner rock abundance images of various craters ranging from Tycho, which has one of the most youngest and rockiest impacts, to older impacts that are impacts that have exposed bedrock that are gradually being pulverized and now showing no thermal signature. This process is very important because it provides insights into the rate at which regolith formation forms, as well as insights into the nature of the transition from the surface layer to the megaregolith down to bedrock. Next slide. Oh, it's set my cursor's back. We've also looked in detail at the thermal structure of impacts elsewhere on the planet, and we've essentially discovered a very large, extensive thermal signature of low thermal inertia material that basically surrounds almost all recent impacts on the planet. This is a very large thermal disturbance that has heretofore not been observed. Extends much more extensively than just the visible evidence of these impacts. And we're currently puzzling over what this could mean. We have a lot of theories involving the emplacement of the ejecta itself. It could be material that was volatile material contained in the impactors, or a bunch of other sort of physical phenomena. But it's very interesting, and we expect that this phenomena is common to all airless bodies. The final major goal of LRO that Diviner has contributed to is understanding the interaction of the moon with its external environment. This is sort of in the case of Diviner, a continuation of looking at the impact record. In this case, looking in detail at how the surface cools off during the night. Turns out that the structure of the regolith impacts this particular parameter, and we can, by carefully tracking the nighttime temperature, get an estimate of how thick this low-density surface layer is as a function of time, and then compare the depth that we determined from Diviner with measurements of ages of crater features, both from radiometric and from impact. Later on today, Rebecca Gent is going to present some of the results of this work, and it's very interesting because we're finally able to put on a rather quantitative footing exactly how the lunar landscape evolved over time. So, in conclusion, Divider's data set is very exciting. LRO is very exciting. The moon itself turns out to be very exciting scientifically. The moon, of course, is just one example of an airless body. It happens to be in orbit around the Earth. It's close by and has a lot of exciting things on it. But it can be thought of at least as a model or a laboratory for studying airless bodies, which, of course, are found all over the solar system and probably all over the universe. All the techniques that we are pioneering with our unique data set in terms of understanding the moon can be and hopefully will be soon applied to many other exciting airless bodies in the solar system. And that's it. Thank you very much.
Thanks very much, David. Wonderful. And your last comments, what a great segue to our own Institute's evolution, where we're expanding beyond the moon. We are continuing our focus on the moon, just to let everyone know, to be absolutely clear. The moon is still a major target for our new Institute. So I believe that Jen Heldman has a question.
Yeah, Dave, I was just wondering if you could say a few more words on how you do the modeling to get the subsurface temperature profiles, particularly for the polar region. Because there are regular properties like thermal conductivity that are very critical to the propagation of the thermal wave and are a large driver. And as you know, this is an important model prediction because it may be driving future polar missions. So I was wondering if you could explain that a little more.
Right. Well, all the papers that have been published on this topic basically use the same technique. You make thermal emission measurements of the surface thermal emission, and then you have a physical model, in this case a thermal model, that then can independently calculate what the thermal emission should be. It calculates surface temperatures as well as subsurface temperatures. When the model and the data agree in terms of surface temperatures, then that gives you some confidence that the subsurface temperatures as well as the thermal properties that the model has calculated are something close to reality. So this is basically the same trick we've been using for years on Mars and applying it to the moon. On the moon, things are quite a bit more complicated because of the fact that you have such a radiatively dominated situation. You've got to get exactly the right amount of calculated sunlight and scattered thermal emission correct, as well as aspects of the roughness of the terrain to really sensibly interpret the data like we get from Divider on an airless body. So it really comes down to how well you can model the data that we've achieved, and that's why we're spending a lot of effort at this stage trying to get the models and the data to better agree with themselves and have some better confidence in our predictions of these properties. So the simple answer is no results yet, but we've got a way to do it, and we're working on it.
Cool. Thanks. I don't believe there are any more questions. I want to remind everyone at Hubs that you can feel free to ask questions verbally. Just let us know in chat. So I don't believe there are any more questions. So thanks again very much, David. Really appreciate it.